Hello and good evening. You're welcome to our last lecture in a series of lectures on statistics for the social sciences. As usual, Amos Peter is my name, and you're welcome to today's lecture. Now, today we shall be discussing about a very important statistical concept, and that is hypothesis testing. And in this class, we shall see what hypothesis is. We shall define hypothesis, and then we shall see the different steps that can be taken in order to conduct a test of hypothesis. As usual, before we start, permit me to share a very interesting quote from one of the greatest physicists that has walked the surface of the earth by name Enrico Fermi. He said, "There are two possible outcomes. If the result confirms the hypothesis, then you've made a measurement. If the result is contrary to the hypothesis, then you've made a discovery." And that's a food for thought. And it is my hope and belief that by the time we end this class today, the meaning of hypothesis and its usage will become deeper and clearer within the context of this quote made by Enrico Fermi. Now, just like I've said quickly, here is the outline. We'll define what hypothesis is, and then we'll talk about hypothesis testing, the definition of statistical hypothesis. We shall see two important types of hypothesis. That's the null hypothesis and the alternative hypothesis. We shall talk about types of error. We shall talk about confidence interval, and then finally, hypothesis testing. But before I proceed, permit me to share the first open class question. The first question, question one, says, what is a z-test, or what is z-test? And then the B part says, what are the assumptions of this test? So this is a very simple open class question, and you can answer that and upload at the appropriate link of the learning management system for grading. Now let's start proper. Generally, what do you mean by the word hypothesis? Now, in science and engineering, and even in the social sciences, a hypothesis is actually an assumption, a premise or a claim that we want to test or investigate. Now, an example is, I can decide to make a premise or an assumption or a statement which says students who eat breakfast will perform better on a math exam than students who do not eat breakfast. Now, this is just a conjecture or a statement or a premise. And then as a social scientist or as a scientist, we want to now then go and sample some of the students in a particular class or college in order to deduce or to find out whether the statement is true or not true. Another example of a hypothesis is to say students who experience test anxiety prior to an English exam will get higher scores than students who do not experience test anxiety. Now, that is that about hypothesis. Now, let's see what is hypothesis testing. As opposed to hypothesis, hypothesis is a noun, while hypothesis testing is the active part, in other words, a verb. And hypothesis testing simply is a systematic procedure that we use to decide whether the result of a research study supports a particular theory, which applies to a population. Now, hypothesis testing uses what we call sample data to evaluate a hypothesis about a population. Now, just like I've written here, it is very, very pertinent to note that the main purpose of performing hypothesis testing is to either accept or reject an initial conjecture that may predict some population parameters based on information from a sample. Now, basically, in doing hypothesis testing, there are two important premises or hypotheses that actually needs to be stated. Now, these are key hypotheses. The first one is known as the null hypothesis, which is being represented by capital H sub 0, or subscript 0 if you so wish. And basically, this hypothesis happens to be the claim or the status quo or the currently accepted value for a parameter. Now, generally, the null hypothesis is actually the de facto. And a quick example is, during the 16th century, when Sir Isaac Newton propounded the laws of motions and gravity, it was said that Newton was just sitting under a tree and all of a sudden an apple, fell on his head. And he began to question what could be behind the apple, falling down. And then he came about the unseen force or gravitational force that pulls every object to the center of the earth. And for a very long time, this very particular claim or assertion held sway, not until in the 19th century when Albert Einstein actually came with an alternative, to theory, which says that it is not actually an invisible or unforeseen forces that actually pull things to the earth, but rather it's as a result of the disruption of the space-time, continuum or fabric that actually makes objects to fall towards the earth. So in other words, that default or the factor claim made by Albert Einstein was later dethroned, and that was the null hypothesis before Albert Einstein. So the Albert Einstein-owned proposition happens to be the alternative hypothesis. And the alternative hypothesis is actually represented by capital H subscript A. And it's also known as the research hypothesis. And actually, it involves the claim to be tested. And it is important to note that the alternative hypothesis can include, some signs such as not equals to, or the less than symbol, or the greater than symbol. It may also contain the less than, or the greater than, and the greater than, or the less than. And it is important to note that the alternative hypothesis may be supported or not supported by evidence that comes from the data. Now, an example of how some of these propositions or claims could actually be stated is as shown. So for an example is that if I make a statement and say the mean monthly cell phone bill in the city of Mexico is mu, is equals to $42. Now this happens to be, let's say, the null hypothesis. Now I could decide to formulate, maybe after I research, another person could decide to say that he has an alternative hypothesis, which could be written this way. HA is such that mu is not equals to $42. So in other words, he is saying, based on whatever research that he or she might have done, that the mean monthly bill in the city of Mexico is not equals to $42. Now, it could also be HA sub A such that mu is greater than $42 and so on and so forth. Now, it is, we sometimes also, we state some of these propositions in terms of proportions. An example is the proportion of adults in this city with cell phone is P is equals 0.68%, expressed as a percentage. And of course, expressed as a decimal. And of course, in terms of percentage, this will imply 68%. So there are times that some of these could be stated in terms of numbers or in terms of proportions. Now, let's quickly see some quick examples of how the null hypothesis and the alternative hypothesis can be stated. Okay. Now, the first example says, it is believed that a candy machine makes chocolate bars that are on average 5 grams. A worker claims that the machine, after maintenance, no longer makes 5-gram bars, and you are asked to write the null hypothesis and the alternative hypothesis. Now, generally, to write them is very simple. Mathematically or statistically, we start with writing the null hypothesis, which is capital H sub 0, such that mu, the average, is equals to 5 grams. This is the default, belief that the candy bar machines actually makes chocolate bars that have a weight of 5 grams. And then now, after some maintenance work, a worker decided to say, no, I don't believe that these very machines makes candy bars that are 5 grams. Then he comes up with an alternative hypothesis and said, HA is such that the mean is not equals to 5 grams. Now, it is important to note that both the null hypothesis and the alternative hypothesis are mathematical opposites of each other. And once we state our null hypothesis and our alternative hypothesis, there are 2 possible outcomes that we could have, statistically speaking. Now, the first outcome is based on our calculations or our research. After we apply all the statisticals to, we can either reject the null hypothesis or we can fail to reject the null hypothesis. And actually, how do you determine when to reject the null hypothesis or failed to reject the null hypothesis? Now, usually we do that through what we call a test statistic. And that could be calculated from the sampled data, and then we can then use that to decide whether we reject our null hypothesis or we failed to reject our null hypothesis. Now let's make progress. Now let's see another example of how to extract our null and alternative hypothesis on some other statistical data that could be given in a question. The second example says a company has stated that their straw machine makes straws that are 4 millimeters in diameter. A worker believes that the machine no longer makes straws of this size, and then went ahead and samples 100 straws to perform a hypothesis test with 99% confidence. And we are asked to write out the statistic parameters. Now, generally, as usual, we always start with our null hypothesis, which we write as H subscript 0, such that the mean of the straw is 4 mm. And then we are told that a worker has an alternative hypothesis, which he believes that the machine no longer makes 4 mm diameter straw. So that means that our HA is going to be such that mu is not equals to 4 mm. Now we are also told that he went ahead and samples 100 of those straws. So in other words, our N is going to be equals to 100. And we are told that he performed the hypothesis test with a 99% confidence. So in other words, it means C, the confidence level is equals to 99%, which in decimal can be written as 0.99. And then, now it is important to know before I proceed that sometimes you may be given the confidence level, and sometimes you may be given what we call the level of significance, alpha. Now, it is important to know that the level of significance, alpha, is related with the level of confidence by the formula 1 minus confidence level. So in this case, since we are given that our confidence level is 99% or 0.99, it means our level of significance is actually 1 minus 0.99, which is equals to 0.01. Now, it is very important to note that in social sciences, generally, we make use of confidence level of 95%, are very common, and 99% confidence level. So in other words, the confidence level is trying to give us an idea of how confident are we in our decision that whatever result we get from the experiment is true or not. Now we shall see how that is being done, even as we proceed. Now permit me at this point to present the second open class question, which says, what is a t-test? And what are the assumptions of a t-test? So you can see that this is very similar with the first. So answer that and upload in the learning management system for grading. Now let's look at the third example, which says doctors believe that the average teen sleeps on average no longer than 10 hours per day. Now a researcher believes that teens on average sleeps longer. And then we are asked to write the null hypothesis and the alternative hypothesis. Now, this is generally written this way. The null hypothesis, H subscript naught, is such that mu is going to be less than or equals to 10 hours. And it is very important for us to look clearly at the statement or the sentence. It says doctors believe that the average teen sleeps on average no longer than 10 hours. This word no longer simply means that a teen could sleep for any number of hours less than or equals to 10, but not greater than 10. So in other words, you can sleep for 1 hour to 2 hours up until 10, but no more. So in other words, that will be represented with a less than or equals to 10 hours, whilst a researcher has an alternative hypothesis which believes that teens on average sleep longer. So in other words, it said, no, teen sleeps longer than 10 hours. So it means HA such that mu is greater than 10 hours. It is important to know that for the alternative hypothesis, it's simply going to be greater than and not greater than or equals to, because here he says he believes that the teen sleeps longer. So in other words, if you put equals to, it makes this very particular statement invalid because that has been included in the first statement. So basically, that is how we do that. So let's make progress. Let's see the fourth example, which makes use of proportion instead of just a straight mean value. Now, it says, the second question says, the school board claims that at least 60% of students brings a phone to school. Then a teacher believes this number is too high and randomly sampled 25 students to test at a level of significance of 0.02. And we are asked to write H0 and HA. And it is important to note that these questions that have been given are just trying to tell us all the different and alternate ways that questions could be framed. You could see, I think in question number 2, we are given the confidence level, but in this case, we are given the level of significance. And of course, I told us that the level of significance and the confidence level is represented using a formula. Confidence level is equals to 1 minus level of significance, or level of significance equals to 1 minus confidence level. So for us to bring out all these, we start with the null hypothesis, which is H0, such that the proportion, the word at least in this case means from 60 and above. It means 60 is also included. So the proportion of student that brings a cell phone is greater than or equals to 0.60 in decimal for fraction. While the alternative hypothesis proposed by the researcher says that P is less than 0.60. And then we're told that the sample he picked was 25. We just want to bring all the data. and we're told that the level of significance is 0.02. So in this case, we can say that our confidence level is going to be 1 minus 0.02. In this case, this implies that our confidence level is equals to 0.98 or 98%. So in other words, this is telling us that we are 98% confident that this student, whatever it is the outcome of the hypothesis, if this is true or this is true, it means 98%. Whenever we sample, let's say 100 students, then we are confident that 98% of them will actually be either among those that brings a cell phone or not, depending on the outcome of the experiment. Now, before we proceed, we are going to see the various steps that will be taken mathematically before we can test a hypothesis. Now, the first step in testing a hypothesis is for us to state the null and the alternative hypothesis, which is what we've been doing all along. So we test our null and hypothesis, alternative hypothesis. Now, the second thing we need to do is for us to choose the level of significance, which is generally or usually at the discretion of the researcher. And then we determine what we call the rejection region. As will soon be seen, we'll determine the rejection region. Now, having done that, we then calculate a test statistic and compare it with the critical values or the rejection region that has been set. And then we state the conclusion by either rejecting the null hypothesis or we failed to reject the null hypothesis. So in subsequent slide, we shall see how those calculations or those values can be obtained. But before we do that, permit me to talk about two important types of error in this case. The first one is known as the type 1 error. And the type 1 error is actually what was referred to, or what is referred to as the level of significance. And is the most serious error that could be made. And this error is also referred to as a false positive. And generally, it is the probability of making, I said generally, the probability of making this error is denoted by alpha, which is the level of significance. And is generally the probability of you or of a researcher rejecting a null hypothesis when in fact it is actually true. So the researcher is actually responsible for ensuring that he tries as much as possible to reduce this type of error. Now, in the case of the type 2 error, is when you accept a false null hypothesis. The probability of making this error is denoted by beta. And it is important to understand that the beta depends on the sample size and the population variance. So these are the two major types of errors that can be encountered whenever we are doing the testing of hypotheses. Now let's go straight ahead with examples of real life calculations and see how all these tests can be carried out. Now the first question says, Dolce Tomate is a ketchup maker. They use a machine to pour 16 ounces of their sauce into bottles. From its many years of experience with the dispensing device, Dolce Tomate knows that the amount of product in each bottle is normally distributed with a mean of 16 ounces and a standard deviation of 0.15 ounces. A sample of 15 bottles filled over the past hour revealed that the average amount per bottle was 16.017 ounces. And then a question was asked, does the evidence suggest that the average quantity dispensed is different from 16 ounces? Use a significance level of 0.05. Now, to find the solutions to this problem, the first thing we need to do is to, like we say, state our null hypothesis and alternative hypothesis, and also bring out all the other statistical data that we've been given. Now, the null hypothesis states this H such that the mu, that's the average, the mean average of the paste inside the bottle is 16 ounces. Now, the alternative hypothesis states that the average or the mean is not equals to 16 ounces. And then we're told that a sample of 15 bottles, so N here is going to be 15, was filled over the past 1 hour. In other words, was sampled, and it was found that there was a standard deviation of 0.15. And then we are also told that the sample mean of the paste was 16.017 ounces. And let's not forget, we are also told that alpha, our level of significance, is 0.05. Now this implies that we are going to have that our alpha byte 2 is going to be equals to 0.025. And I will explain how we got that in this next slide. Now, generally, from our previous lecture, when we were talking about normal distribution, we said that generally most distributions in nature actually follow this kind of shape. With a mean of 0. And actually, we said that for a normal distribution, this is going to be a symmetrical shape with the left-hand side exactly equal to the right-hand side. Now, and we said that when we are carrying out testing of hypotheses, we will also calculate what we call our critical values. So let's assume we have a score at this point, especially for a two-tailed test, where here is going to be our Z alpha to the right, and then we also have this. We also have our Z alpha to the left. Now, it is important to know that all the areas under this very particular curve, in other words, the areas here, let me start with the areas here. The areas here are actually the areas in our rejection region. So in other words, when we calculate our Z statistic and we compare it with our Z critical, and the number is outside all these values, then we actually reject our null hypothesis. If it is not, then we failed to reject our null hypothesis. Now, it is important to know that this is alpha, but because it's a symmetry, of course, this is going to be our Z alpha. This side is going to be alpha byte 2, and here is also going to be alpha byte 2. And of course, the number here is going to correspond to our confidence level. So it is important for us to know that alpha byte 2 plus alpha byte 2 plus the confidence level, all the area under this must be equals to 1. Now, it then means that we need to calculate our Z critical value at, so now we calculate our Z critical value. The critical value, which is Z alpha byte 2. which could also be written as C of 0.025. And basically, how do we do that? Yeah, well, there are different methods or formulas, and generally, this could actually be obtained as the area of the curve to the left of this Z alpha. So in other words, all these areas, that is this plus this, that are to the left of Z alpha. So in other words, the area, if you like, area to the left can actually be given by this formula, 1 plus confidence level divided by 2. Now, and it is important for us to know that, let us not forget, we are told that, I told us that confidence level could be given as 1 minus alpha. So it then means our confidence level in this case will be 1 minus, and our alpha is what? 0.05. And of course, 0.05 will give us what? Let's see what that gives us. Excuse me, please. So that gives us 0.95. So this then implies that we are going to have 1 plus 0.95 divided by 2. So this implies that area to the left, which is the same thing, let's not forget, at Z of alpha by 2, or 0.025, is going to be, if we add that gives us 1.95. And then divided by 2. That gives us when we do that divided by 2, if that is divided by 2, that gives us a value of 0.975. Now, in other words, what this is telling us that at this very particular value of 0.025, that's Z alpha at 0.025, the area of the curve to the left of this is actually 0.975. Now, having got that, all we need to do, we then convert the area to the left of AL, which is 0.975, to the Z-score using the Z-score table. And how do we do that? Permit me to quickly move to our Z-score table and see how that can be done to the last. So you look at the table of Z distribution. We are looking for a value that is 0.9750. And here is the number, obtained here. Now, all you need to do is just for you to look at exactly at the top vertically and horizontally where these two numbers actually meet. So you can see that to the left of 0.975, it is 1.9, and vertically to 0.975 is 0.06. So it then simply means that our Z value is going to be 1.9 plus 0.06. And that is going to give us the Z value at alpha 0.025 is equals to 1.96. So if we quickly go back to this, our value at this point from the Z table is going to be 1.96. Now, I haven't done that. I haven't obtained that as 1.96. Now, the next step that we need to do is for us to find our Z calculated. So in other words, but let me just draw here what the Z critical actually implies. If this is our distribution again, what this is simply telling us is that this to the right here is 1.96, while to the left here is minus 1.96. And of course, this is mu. Now, this is our Z critical. And we are now going to calculate our Z calculated and then compare it with the Z critical and see whether it is within the rejected region or failed to reject region. So to find our Z calculated, the Z calculated can simply be obtained from this formula of Z score. Z is equals to X bar minus mu all over sigma divided by the square root of n. And of course, what this simply means, from all our data, we've been given that X bar is 16.017 minus mu, the population mean is 16, all over the standard deviation is 0.15 divided by the square root of the sample n, which is 15. And of course, if you do the math neatly, you should find that Z calculated is equals to 0.44. Now that we've gotten that our Z calculated is equals to 0.44. Now the next thing we need to do is for us to compare that. Now let's not forget that for a normally distributed data, the mean is actually equals to 0. So you could see that our 0.44 will be somewhere here. If this is 0 and we're moving to the right, our 0.44 will actually be somewhere here, 0.44. And you know, we've been able to set that all these are our rejection region. So if our data had fallen on the right-hand side of 1.96, we are supposed to reject the null hypothesis. And if our data had also fallen to the left of minus 1.96, we are also supposed to reject our null hypothesis. Now, but since the data is not within the rejected region, is within here, then it simply means that we fail to reject the null hypothesis. So you can see here, I said, what is your decision regarding the null hypothesis? Then I went ahead to say that H sub naught is not rejected. And the interpretation is that it is not possible to conclude that the average amount that is being dispensed into the bottle is different from 16 ounces. So in other words, our null hypothesis still stands. Now let's make progress. The second example here says a vendor claims that the average weight of box is 1.84 kilogram. And then a customer randomly chooses 64 parts and find that the sample weight is 1.88 kg. And suppose population standard deviation is 0.3 kg, and we're asked to use an alpha value, that's level of significance, of 0.05. And then we're asked to use that and test for the hypothesis that the true mean of shipment is 1.84 kg. Now, as usual, we collect our data. So we start with our null hypothesis, which will set H sub naught such that the mean weight is equals to 1.84 kg. And then our alternative hypothesis such that mu is not equals to 1.84 kg. And we're told that alpha, our level of significance, is 0.05. Now this implies that our alpha byte 2, as explained in the previous slide, is 0.025. Now the next thing we need to do is for us to calculate our Z critical. So our Z critical, which is the same thing as Z at alpha byte 2, which is the same thing with Z at 0.025, just as we've done before. So that's going to be 1 plus 0.95. How I got 0.95 was already shown in the previous slide, divided by 2. And that's going to give us 1.95 divided by 2, which finally is going to give us 0.975. Let us not forget that Z critical is still the same thing represented as area to the left of our normal distribution curve. And then, of course, I told us that the next thing we need to do is for us to convert the area to the left. That's the 0.975 to the Z score. And when we do that, as before, using the Z distribution table, we obtain that that is equals to 1.96. Now, the next thing we need to do is for us to find our Z calculated. So it then means that our Z calculated from the Z score formula is going to be, as usual, X bar minus mu all over sigma divided by root n. And of course, we have that our X bar has been given sample mean as 1.88 minus the population mean 1.84 divided by standard deviation 0.3, and then divided by the number of samples, which is 64. And of course, if you do the maths neatly, you should find that Z calculated is equals to 1.07. And then this could be represented pictorially like this. So if we have, as usual, our Z distribution curve, then means that this 1 point, what we've gotten, we are going to have the 1.96 minus 1.96 here. And then we've been able to find that our Z calculated is 1.07, which is, and these are the rejection region. Well, here we have 1.07. If this is 0, this is, let's say 1.07 is still within, just before the rejection region. So in this case, our conclusion is that we failed to reject the null hypothesis. In other words, the null hypothesis still stands, that our mean sample weight for the box is 1.84 grams. So our conclusion, or the decision, is that we failed to reject null hypothesis. Now let's make another progress and see here where we are going to make use of a t-score as opposed to a z-score. And I will quickly tell us why we have to use a t-score, so that we can easily know when to apply a t-score and when to apply a z-score. Now the question says a machine produces parts with mean length of 4.125 mm. Customer randomly chooses 20 parts and finds sample length as 4.120 millimeter. Suppose the sample standard deviation is 0.008 millimeter, and we are asked to use the level of significance as 0.10 to determine whether the mean length has decreased. Now, the first thing we do, let's also collect our parameters and see. So the first, we state our null hypothesis, H sub 0, such that the mean length is 4.125 millimeter. And then we have our alternative hypothesis, such that it says the mean length is less than, as you can see, this was the original mean length, 4.125. And when it was sampled, it was 4.120. It means, and you can see that this is less than this. So mathematically speaking, simply the alternative hypothesis simply means that HA is such that mu is less than 4.125 millimeter. And we're told that our alpha is equals to 0.10. Now, generally, if these conditions are met, that is when our population mean is not known, and when our samples are small and usually less than, let's say, 30, then use t-scores or t-test. So basically, that means that here we are going to determine what we call our t. So let's move here. We are going to start by determining what we call our t critical as opposed to z critical. So we have three critical, which is represented as t at the level of significance and the degree of freedom, which is n-1. So in other words, this is going to be written in this form as t at level of significance, which is 0.1, and the degree of freedom, which is the number of samples minus 1. So in other words, the number of sample is 20 minus 1. That gives us 19. And so this implies that t at 0.1, 1.9 will be obtained directly from the t table. So permit me to go straight to the t table. You can see here's the t table. So, and we want to find t at 0.1 and 19. Now, all you need to do is that the t at 0.1, you can see here, vertically we have t, and this is 0.1. And then here is the probability of the one tail. So you can see here we have the degrees of freedom, which is 19. So you simply look at 19, which is your n minus 1, 20 minus 1, 19. And then you also look at where it intersects with 0.10. So you can see when I neatly drew a line here, everything intersects at 1.328. So let's quickly go back to our thing and see that the value we are going to have here is 1.328 from the t table. Now, since this is a one-tail test, and of course, this is because of the alternative hypothesis. We said that the mean is less than 4. So it can never be greater than 4. But when we say that the mean is not equals to 4, it means that the mean could either be less than 4 or greater than 4. Hence, we are going to have a two-tail, one to the left and one to the right. But in this case, it simply say that the mu is less than 4. Then it then means that we are going to have just a one-tail test to the left. So in other words, this 1 point, I'm going to have minus 1.328. And of course, you can see that our mu is actually equals to 0. So it then means that any value here to the left of this guy, we reject the null hypothesis. But for values to the right of this guy, we actually failed to reject. We failed to reject. Now, the next thing we will do is for us to calculate our, this is the t critical, so we'll now calculate our t calculated. And the formula is similar to that of the z distribution. So it's going to be x bar minus mu all over s. And of course, this is going to be 4.120 minus 4.125 all over 0.008 divided by the root of 20, because 20 parts were sample. And of course, if you do the math very well, you should arrive at your t cal, as the calculated value of t is minus 2.80, minus 2.80. Now, it is important to know if to the left here is minus 1.328, then of course, minus 2.80 should also be somewhere here, minus 2.80. And you can see that it is to the left-hand side, that's outside the rejection region. So in this case, that our conclusion here is that we are going to reject the null hypothesis. In other words, this hypothesis has been shown that the machine does not produce rods with mean length of 4.125. So our decision here is we reject the null hypothesis. And basically, that is how all these statistical tests are being carried out. And it's a very important and formidable tool that helps researchers across different disciplines, either in the social sciences or engineering, to be able to arrive at a scientific and a technical way of either accepting a proposition or rejecting a proposition. So I think we've come to the end of this lecture. And before we call it a day, permit me here to share the last open class question, which says that assume the cholesterol level in a certain population have mean mu equals 200 and standard deviation sigma 24. The cholesterol levels for a random sample of n equals 9 individuals are measured, and the sample mean x is determined. Now, what is the z-score for a sample mean? Now, all you need to do is just for you to select from any of these options and upload your answer in the learning management system for grading. Now, I hope that the information that has been provided here in this lecture has been very, very informative. It's rather unfortunate. I can see that our time is fast spent. Otherwise, I wanted to review the case study number 3. But if I'm to review that, I think that will drag the length of this video to more than 1 hour. So anyway, I hope that the information is very informative, and I would like to thank you for viewing. So try as much as possible to complete your remaining activities, because this is the last week before this course is finally closed. So try and submit all your activities before the end of this course. Thank you very much, and I wish you good luck and a happy night rest. Bye-bye.